Hi budding engineers, welcome to Structural Engineering Lectures and welcome to the new playlist on the DesignofSteelStructures conforming to IS 800 2007 limit state method. In today's class we shall see the design of compression member as a column, as a stanchion, right, wherein we will see how to select a suitable I-section, as well as if a section is given, how to determine the load on it, right? These two problems we'll see, right? The first problem is we will calculate the load on a given I-section. Second one, the load is given, how to propose a section, how to propose the design, right? Both of these problems we will see. Whereas in the previous class we have seen the design of compression member, right? Section classification, flexural, local, torsional, buckling and effective lengths, and all the IS 800 2007 limit state method specifications. I hope you enjoyed the discussions there. If you really enjoyed the discussions, right, don't forget to click like, share, subscribe and comment to our YouTube channel. Now let us see the brief profile of the speaker, that is I, Dr. D. Rupesh Kumar. Has obtained my BTech Civil Engineering from Nagarjuna University in 1994, MTech Structural Engineering from JNTU Hyderabad in 2000, as well as the PhD in Structural Engineering from JNTU Hyderabad in 2009. Presently I am working as Professor of Department of Civil Engineering, University College of Engineering, Osman University, Hyderabad, Telangana State. I have an experience of 27 years, of which 7 years is in industry and 20 years is in teaching and research at graduate and postgraduate levels. My research areas include reinforced cement concrete design, steel structural design, structural analysis, plant element analysis, earthquake engineering, bridge engineering and structural optimization. I have published 45 research papers in national as well as international journals and conferences, organized 3 international conferences and 11 national conferences and workshops, attended 43 workshops and visited 2 countries and delivered 13 guest lectures and edited 3 books. And supervising 14 PhD scholars and supervised 30 ME theses, right? I am actively involved in various consultancy works that are offered by the department and have completed over 750 design proof checks and 150 plus designs of the reinforced cement concrete, steel, composite, low-rise, high-rise and multi-shored and road and rail bridges, right? And I am an executive council member of the Indian Concrete Institute Hyderabad Center, right? Now, once we see this brief profile, student, let us move quickly to the topic what we'll be discussing, right? In the previous class, we have seen all the codal specifications pertaining to the designs of the compression member, right? Now, this is we'll now see a numeric problem, wherein the first problem is calculate the design compressive load for stanchion ISHB 350 at 710.2 Newton per meter, whose length is equal to 7.5 meter. The column is restrained in position at both the ends, right? It is to be used as uncased column in single storied building. Use Fe 410 grade steel, right? This is how a section is given, student. Let me just show, right? This is how a section is given, ISHB 350, right? And wherein at the top as well as at the bottom it is restrained in position, right? Restrained in position, right? That is how it is given. Therefore, now you are supposed to calculate how much load this column can carry, or like this, right? How much this load this column can carry, right? Therefore, now let us see what is the data given, right? Therefore, if I see from IS 800 2007 table 11 page number 45. Now let me go to that page number 45, student, right? This is how the page number 45 of IS 800 2007, the effective lengths of the prismatic compression member, table 11, wherein it is given that both ends are restrained, right? Therefore, there is a restrained at the top against a translation at one end as well as rotation, at the other end also restrained in translation as well as rotation. Therefore, for which this is how that it is case, means it is fixed at both the ends, both the ends, like this, right, student, right? This is how fixed at both the ends. Hence, the effective length from this codal specification is equal to 0.65. Therefore, I'll just recalling this data and written here. Therefore, the effective length factor K is equal to 0.65 multiplied by the actual length. Actual length is equal to 7.5. It now works out, say, 2.275 meters, student. However, from IS 800 2007 table 46 page number 138 for ISHB 350 at the rate of 710.2 Newton per meter, what are the relevant properties? Let me go to this page number 138, student. Just bear for a moment, right? 138, right? 138, yes. ISHB 350 right? This is that section, student, right? ISHB 350 at the rate of 710 Newton per meter. 710 Newton per meter. Now in this IS 800, what is given? This is in terms of kg per meter, right? So, weight is in terms of kg per meter. Therefore, I'm just noting down the relevant properties, right? This is that area is 92.21 centimeter square, and the depth of the section is 350, and width of the flange is equal to 250, right? And the thickness of the flange TF is equal to 13. And the thickness of the web is equal to 8.6, right? Radius of variation, right, is equal to 16.6 centimeter. About the major direction as well as the minor direction is a 4.04. I'm just recalling this data. I just copied and pasted here, right? This is how that data is recalled here. And what is also given is a use Fe 410 grade steel. Fe 410 grade steel. Therefore, the ultimate strength of this steel is equal to 410 Newton per mm square, student, and Fi yield stress is equal to 250 Newton per mm square. And also from the table 5, page number 30 of IS 800. Let me go to that page number 30. Let me go to that page number 30. Right now, this is how page number 30, students, right? Wherein now I do have this table, wherein from this table the partial safety factors are available. Therefore, this is how I am recalling these partial safety factors from this table 5, student, right? Therefore, the partial safety factor gamma m naught is against the yielding 1.1, and as well as for ultimate the partial safety factor for ultimate stresses is equal to 1.25. Therefore, I recall the data from the codal specification. Now, first subheading is the section classification for rolled steel I section. Please make a note that we are using the rolled steel I section, right? Like this, right? I'm just showing that of the flange as well as the web part of this, right? Flange as well as web part, right? Similarly, up to the neutral axis I'm showing, right? And so, what is that H by BF, right? H is already given. The depth of the section is given as 350 mm, and width of this flange is equal to 250 mm. Therefore, now it works out 1.4, which is just greater than 1.2, and the thickness of this flange is equal to is less than 40 mm, because just now we have seen that thickness of the flange from the IS 800 is equal to 11.6 is much less than 40 mm. Therefore, now what I'll do is I'll go to this table 10, page number 44 of IS 800. 44, right? Yes, student, right? 44, just a moment, right? This is the table 10 buckling class of cross section. Now we are there in rolled steel I section, student, right? Wherein H by B is greater than 1.2 and thickness of the flange is less than 40 mm. Therefore, the buckling class about the major axis, the horizontal axis is the major axis, right? Wherein about this axis it is the buckling class is A, and about the vertical axis, which is the minor axis of bending, about this class it is B, right? Therefore, now once I note down this, now that is how my buckling class is defined about both the axes, right? A and B respectively along the major and minor axis. Then we already know that design compressive strength is generally governed about the minor axis. We already know, right? Therefore, now nevertheless, what we'll try to do is we'll try to calculate about both the axes, right? About the major axis as well as about the minor axis, right? Using the tables as well as the formula, as well as the table 9A, 9B, 9C, 9D, as well as using the tables 8A, 8B, 8C, 8D, as well as using the formula. Therefore, all the three will see this being the very first problem. Right now, this is the next subheading is the design compressive strength, either using the formula or using the tables. Right now, first we'll try to see what is the design compressive strength using these tables 8A, B, C, D respectively. For which, what I need to do is I need to calculate the slenderness ratio, which is defined as effective length to the radius of variation. Now please make a note, the student, I am just calculating this about the minor axis, because now I am showing that once the load is applied on this web, right, now you can see that this is buckling. First, primarily it is buckling about the minor axis. It is not buckling about major axis. Right? Now you can see it's buckling about minor axis. Therefore, now I'll calculate about the minor axis. What is R min, right? R min. we have seen that about major axis the radius of gyration is equal to 146.5, whereas about the minor axis it is 52.2. Therefore about minor axis r min is equal to 52.2, and k we already seen 0.6 multiplied by 3500. Now it works out say 43.58. However, now what I'll do is I'll go to this table 8A, page number 36 of IS 800, page number 36, right? This is page number 36. Bear for a moment, right? 36. This is the I'm there in table 8A, stress reduction factor, right? Stress reduction factor for column for buckling class A, right? Whereas you please see that here we are there about the minor axis. Now we are there about the minor axis, therefore I shall use this B is applicable for the buckling class B. Therefore now I need to go to that wherein I'll recall that value, I'll interpolate, right? Therefore this is how I'm recalling. Okay, we'll do that like this, right? However, I'm showing this about using this table 8A, student, about the major axis actually, right? These are the values I have recalled for slenderness ratio. At 40 and 50, these are the values 0.934, 904, right? These are what seen for 40 and 50. Actually, I'm using 8A. For minor axis, I should be using 8B. However, I'll show that later, right? This is how, once I know this value for slenderness ratio, lambda is equal to 0.939 and lambda is equal to 50.904. Now I can interpolate in between. Therefore, I'm just interpolating this for my required value of 43.58. It is how much? Therefore, that value is equal to this base value 0.939 minus this difference, this difference of 0.939 minus 0.904 over a difference of 50 minus 40. However, over 43.58 minus 40. Therefore, that works out. The stress reduction factor will work out 0.92647. Right? This is using the table 8A. However, for minor axis, we should be using about minor axis 8B. Similarly, we'll see about minor axis this stress reduction factor. Right? Now let us see that what I am now showing, right? Therefore, if I go to this table 9B, page number 41. Now let me go to this page number 41, student, right? Wherein now I am there in page number 36. Just bear for a moment, right? Yes, this is page number 41, right? 41, wherein this is 9B. Previously, we should have used about minor axis 8B. Therefore, corresponding to that, I shall be using 9B. Therefore, the design compressive stress FCD in MPa, Newton per mm square, for column buckling class B. Because about minor axis, it is column buckling class B. Therefore, we know slenderness ratio is 40 and 50. Therefore, for slenderness ratio 40, FCD value is equal to 206, and for lambda is equal to 50, it is 194. Therefore, I need to interpolate for, this is for Fi is equal to 250. Like this, you please see FC, the yield stress of the steel is given from 200 to 540. Therefore, I am there in Fi is equal to 250. For that, the values for lambda is equal to 40, 206, lambda is equal to 50, FCD is equal to 194. Now I'll interpolate. Therefore, I have just copied and pasted here. Therefore, for lambda is equal to 43.58. That value is equal to how much? Therefore, that interpolation will be done like this. Right? The value is reducing, right, from 206, right? 206 to 194. Therefore, 206 to 194 over a difference of 10. Therefore, over a difference of 3.58. How much is the reduction? Therefore, that is deducted from 206. Therefore, now I get 201.7 Newton per mm square. Therefore, once I get the permissible design compressive stress, hence the load carrying capacity is equal to gross area multiplied by permissible compressive stress over the gross area. Therefore, 201.7 multiplied by 9221 divided by 10 to the power 3, because the area is already noted from IS 800 table, student, right? That is, the area is equal to 9221 mm square. Therefore, now if I divide with 10 to the power 3, now I'll get in terms of kilonewtons. Therefore, that value works out, say, 1859.8 kilonewtons, say approximately 1860 kilonewtons. About the minor axis, it is just able to carry 1860 kilonewton only. Now let us say about major axis. Obviously, about major axis, this is the load carrying capacity is more, right? Is more, but nevertheless we'll see how much is the more, right? And we'll prove that from fundamentals also. Therefore, however, about the major axis or strong axis, right, the buckling class is A. Therefore, if I go to this table 9A, now I do have from page number 40, right? I'll just interpolate the values like this, right? I'll interpolate, just bear for a moment. Therefore, I'm there in table 9A, student, right? For 40 and 50, the values for 250 are 213 and 205 respectively. Therefore, upon interpolation, right? I'm sorry, student, right? Whereas I need to calculate afresh the slenderness ratio about this major axis. I'm sorry, right? Therefore, the slenderness ratio about the major axis is equal to effective length 0.65 multiplied by 300, whereas the radius of gyration about major axis is 146.5. Therefore, the slenderness ratio about major axis will work out 15.53. However, now this 15.53 lies in between 10 and 20. Therefore, now for 10, what is that value? For 20, what is that value from table 9A? Therefore, these are respectively, right? These are respectively, you please see, I'm there in table 9A, because about major axis is a buckling class A. Therefore, for 10, for Fe 250 grade steel, for 10, slenderness ratio 227, and for lambda is equal to 20, the FCD value is equal to 226. Therefore, now interpolate. Therefore, you know how to interpolate that. For 15.53, it is how much? Therefore, that now works out, say, a value 226.45 Newton per mm square. Therefore, the load carrying capacity about the major axis is equal to AG multiplied by FCD, that divided by 10 to the power 3. That works out, say, 9221 multiplied by 226.45 divided by 10 to the power 3, 2088 kilonewton. Now, whereas about the minor axis, it was just around 1860 kilonewton only. Whereas here about the major axis, you can see almost, right, 1860 means almost 430 kilonewton is more. 430, almost we can say that approximately 20% is the more load carrying capacity about the major axis, right? But out of these two, whichever is minimum, therefore about the minor axis, the minimum value is governed by the minor axis, which is 1860 is the design compressive load. Design compression load is 1860 kilonewton, right? This is how, using the tables 9A, B, C, D, we have seen, right? Now similarly, now we'll see, right? We'll see using another alternative procedure, student, right? FCD calculation using the formula. Therefore, now if I see this IS 800 2007, if I go to this IS 800 table 7, page number 35, using this formula, let me just go to this formula, right? I am there in page number 35, student, right? Let me go to that page number 35, right? This is using the formula. The code says that the formula is this one. The other day we have seen already this formula, student. Design compressive strength, right, is like this, right? P should be less than PD, where PD is equal to AC multiplied by FCD. This formula just now also we have seen, where AC is the effective sectional area and FCD is the design compressive stress, that we have seen. Therefore, the design compressive stress FCD of axially loaded compression members, FCD is equal to Fi divided by gamma m naught, that divided by pi plus square root of pi square minus lambda square, which is equal to x multiplied by Fi divided by gamma m naught, which should be less than or equal to Fi divided by gamma m naught, right? Where pi is a parameter which is given by 0.5 multiplied by 1 plus alpha multiplied by lambda minus 0.2 plus lambda square, and where lambda is non-dimensional effective slenderness ratio, right? It is not KL by R. It is non-dimensional. Please make a note, student, right? Which is given by square root of Fi divided by FCC. Whereas that FCC is Euler's buckling stress. This we already seen in strength of material, right? Euler's buckling stress. Euler's buckling stress or Euler's buckling strength, right? Pi square E divided by lambda square, where lambda is equal to KL by R whole square. Effective slenderness ratio KL by R whole square is the effective slenderness ratio KL by R as appropriate radius of gyration, and alpha is an imperfection factor as given in this table 7. We'll see that, right? Where X, Roman X is the stress reduction factor as given in this table 8A, B, C, D, right? There it is for different class. We have seen 8A is for class A, 8B for B, 8C for C, and 8D for D class, right? And for appropriate buckling class and for appropriate slenderness ratio and yield stress. These 3 parameters we have just seen, right? Which is calculated using this formula 1 divided by pi plus square root of pi square minus lambda square, student, where lambda m0 is the partial safety factor for the material of the strength. Whereas now the code says that this stress reduction factor is presented in this figure 8, right? That now we'll see. Whereas this imperfection factor alpha from table 7 for different buckling class, let us say for buckling class A, alpha is equal to 0.21, right? B 0.34, C 0.49, and D 0.76. Whereas if you know now, the code says that you go to this figure 8. Therefore now column buckling curves for FCD divided by for different values of effective slenderness ratio varying from 0 to 3 for different buckling class A, B, C, D. Therefore, once you calculate that accordingly, let us say if that value is equal to 1, therefore let us say the buckling class is equal to A, then approximately that FCD by Fy is equal to 0.6263. Therefore, this is how FCD by Fy can be calculated, where FCD can be arrived at, or alternatively even you can use these tables 8A, B, C, D respectively also, right? Therefore, now let us see this, right? Therefore, once we see this, just now we have seen from this table 7 for buckling class B. For buckling class B, alpha is equal to 0.34. Let us revisit this, right? For buckling class B, alpha is equal to 0.34, right? This is how, right? Whereas for buckling class A, it is 0.21. Therefore, about minor axis, this is buckling class B, student, right? Therefore, for about minor axis, it is first I am calculating about minor axis, where the buckling class is B, alpha is equal to 0.34. Hence this lambda actual slenderness ratio, right? 0.65 multiplied by 3500 divided by R. About minor axis is 52.2, which works out 43.58. We have seen in the previous discussion also. Whereas lambda is equal to square root of Fy divided by FCC, where FCC is the Euler's buckling strength given by pi square E divided by lambda square, where just now we have calculated lambda for 43.58 whole square. In the denominator, the numerator pi square E, the default value of Young's modulus of the steel is 2 × 10 to the power 5 as per this code. Therefore, substituting which now we get 1039.3 Newton per mm square is a Euler's buckling stress. However, substituting these, now I can get the non-dimensional slenderness ratio given by this square root of Fy is equal to 250 divided by 1039.8. It works out, say, 0.49. Therefore, now I'll substitute that lambda here in this formula to get pi as 0.5 multiplied by 1 plus alpha is equal to 0.34 multiplied by lambda. Just now we have obtained 0.49 minus 0.2 plus 0.49 whole square. Therefore, it works out, say, 0.66935. Once I get this, now I'll substitute here, right? Therefore, that the lambda is already known, 0.49. Therefore, substituting which now I'll get the permissible bending permissible axial compressive stress or direct compressive stress. Both are same. Fy divided by gamma m0 pi plus square root of pi square minus lambda square. Substituting which now I'll get, right, 250 divided by 1.1 divided by 0.66935 square root of 0.66935 whole square minus 0.49 whole square, or it works out, say, a value 901 0.96 Newton per mm square, but the code says that it should be less than or equal to Fi divided by gamma m naught, 250 divided by 1.1 or 227.27 Newton per mm square. But what the value we got, 201.96, is much less than that permissible value. In any case, it cannot be greater than upper bound value. Upper limit is equal to 227.27. Therefore, it is okay. Hence, I can use this value. Let us say if this value is equal to, now let us say after calculation you got some value as a 231.96. Therefore, it is not advisable. You restrict that value to 227.27 only. Therefore, don't use the 231.96, but you use 227.27 student only, right? Therefore, now this is okay, this value is okay. Hence, substituting with, now I'll get the 201.958 multiplied by that area of the section. Already we have seen in the previous case, like this side, like this 9221, that will be 10 to the power 3. It works out a value 1862.25 kilonewton only, right? Whereas using the table in the previous case we got 1859.8. hardly it is differing by a value of 2.45 kilonewton. Therefore, compared to that of this 1860, hardly it is even 0.01 percentage, which is negligible error. Therefore, I can neglect that small change, right? Because the table as well as this curve as well as the table 8a b c d are this curve, right, or that of the table 9a b c d, all will give the same value, right? All will give here and there the same because of this decimals only, right? Decimals only, there is a small change in error, right? Therefore, it is okay. However, even if I calculate using the same formula about the major axis, now I'll calculate the load carrying capacity of this column about the strong axis or major axis, about which it is a class A, buckling class A. Therefore, from table A, just now we have seen in the previous case that about for class A it is a 0.21, right? Therefore, this is a 0.21. Right, this is of 0.21. Therefore, once I know that 0.21 value, therefore now I'll calculate what is the slenderness ratio about major axis. It is already proved that 0.65 multiplied by 3500 divided by 146.5 will work out 15.53, right? That once I have that value, right? Student, there is a writing error here. Actually, this k is 0.65, not 0.6, student, right? There is a writing error here, right? Therefore, now I'll get this non-slenderness, lambda value as square root of Fi divided by FCC, right? Where FCC we already calculated in the previous case, right? Pi square E divided by lambda square. Therefore, now lambda is equal to 15.53, actual slenderness ratio. Substituting which, now I'll get this FCC as Euler's buckling stress or Euler's compressive stress or Euler's compressive strength, all are same, right? Or buckling load, buckling stress, right, is equal to 8184 Newton per mm square approximately. Therefore, substituting which, now I'll get this non-dimensional slenderness ratio, lambda is equal to square root of 250 divided by 8184.4, say a value 0.17477. Therefore, substituting which, now I'll get this pi value is equal to 0.5 multiplied by 1 plus 0.21. Lambda is 0.17477 minus 0.2 plus 0.17477 whole square. It works out as 0.5126. Therefore, substituting into this formula, now I'll get direct compressive stress FCD is equal to Fi divided by gamma m naught is 250 divided by 1.1 divided by 0.5126 plus 0.5126 whole square minus 0.1748 whole square. It works out approximately 223.52. It should be less than or equal to Fi divided by gamma m naught. Just now we have seen that worked out 227. It worked out 227.27, student. Just now we have seen this value. Therefore, this 223.52 is less than the 227. It is okay. Therefore, the load carrying capacity about the major axis is that FCD 228.52 multiplied with this gross area, that will be 10 to the power 3. Therefore, it works out say 2107.18 kilonewton, whereas this is using this formula as given this IS 800, whereas using the table 9A, what we calculated in the previous subheading is 2088 approximately. Therefore, hardly there is some error, right? 19.18 kilonewton is the error, as against a value base value of approximately 2100. Therefore, this 20 divided by 2100, hardly there is a 0.1% error, therefore which is negligible, right? Which is negligible, right? It can be neglected, right? Now, whereas now this is the second option, whereas even alternatively we can calculate using the stress reduction factor. This is alternatively the third procedure I am explaining, right? However, all the three procedures need not be used, right? Any one of the procedure can be used for calculating the strength about the minor axis only, right? You may get a doubt, sir, why only minor axis is having the less load, why not major axis? That's why I'm explaining it elaborately about minor axis as well as major axis using all the three. One formula using the tables 8A, 8B, 8C, 8D. Now I am using those tables 8A, 8B, 8C, 8D using the stress reduction factors, right? Therefore, if I go to this table 8B about the minor axis, it is the buckling class B. Therefore, table 8B is applicable from page number 37. Let me go to this page number 37, students, right? Therefore, I am there in this table, page number 35. Therefore, this is what the table 8B, right? 8B, right? Therefore, lambda 40 and 50, these are the values 0.906 and 0.855. Therefore, if I interpolate, right? Therefore, this is 0.906 and 855. Therefore, for 43.58 slenderness ratio, what is that value? Therefore, it now works out 0.906 minus this difference 0.906 minus 0.855 over a difference of 10. Therefore, over a difference of 3.58 is how much? Therefore, it works out, say, the stress reduction factor will work out 0.8877 is non-dimensional value, right? It just means that one basic value will 1 is 100%. Therefore, now reduction means 88.77%. Hence, it is called stress reduction factor. Sorry, student, right? Therefore, one basic value 100% will reduce, right? Will reduce approximately by reduction is a 12%. Therefore, this reduction factor is 88.77% or 0.8877. One has reduced to 0.88 approximately. Therefore, the FCD, the compressive strength in the design compressive strength of purely axial compression member, right, is the stress reduction factor Fi divided by gamma m naught. Therefore, 0.8877 multiplied by 250 divided by 1.1. It works out, say, 201.76 Newton per mm square. Even using the table 9A also, I got a same value 201.75. Therefore, the load carrying capacity, right, or permissible design compressive stress is FCD 201.76 multiplied by AG gross area, that will be 10 to the power 3. It works out 1860. Even previously also I got almost 1859.8, almost the same value. Therefore, there is no change in the results about the minor axis. Similarly, you can do for the major axis. It is the buckling class A about the major axis. Therefore, from table 8A of IS 800 2007 from page number 36, for lambda is equal to 10 and lambda is equal to 20. Let me go to that. These are respectively, these are stress reduction factors are respectively. This is how that student, right? For Fi from table 8A, stress reduction factor Roman X for column buckling class A. For lambda is equal to 10, this is 1, lambda is equal to 20, it is 0.994. For Fi is equal to 250. Therefore, in between, now I want a value for 15.53, it is how much? Therefore, if I do interpolation, I will get that value as 0.9967 approximately. Therefore, the permissible design compressive stress is equal to stress reduction factor 99.67% multiplied by the base value 250 divided by 1.1. That's the maximum permissible design compressive stress is 250 divided by 1.1, which is 227.27, right? Therefore 226.5, which is less than, which is obviously less than 250 divided by 1.1, which is 227.27 Newton per meter square. Hence it is okay. Hence the design compressive stress about the major axis is equal to this 226.5 multiplied by gross area, that will 10 to the power 3. It works out 2088.5. Even previously also using that table 9b, I got 2088. Hardly there is some difference, student. Therefore, using all the three tables, 8a, 8b, 8c, I have shown. Table 9a, b, c, d, I have shown. Even 3, even I have shown using the formula, right? Therefore, all the three are giving almost sharing the same results. Therefore, the load carrying capacity about the minor axis or the weak axis of buckling is the value 1860 kilonewton for the given, for this given column, student. Let me show this column, right? This is how that column is given, student, right? Therefore, now we have calculated that this column of ISHB 350, it can carry only 1860 kilonewton about this minor axis of buckling, right? Minor axis of buckling, not major axis of buckling, right? That is how. Once I calculate this, now I hope you understood this problem. Now we'll move to the next problem, student, right? You need not do using all the three procedures, student. Just this being the very first problem, I have shown all the three procedures. But in the next design problem, I'll directly either use this table 8 or table 9 or that of the direct formula, either of the three procedures only, right? Now, generally I'll be using this table 9a, b, c, d, because directly there I do have the permissible design compressive stress FCD value for the slenderness ratio. Now this is the second problem, student, right? Design a stanchion, a compression member, right, whose unsupported length is equal to 3.5 meter in a building subjected to a factored load. This already factored. Pu is equal to 250 kilonewton. Both the ends of the stanchions are effectively restrained in position as well as in direction. Means it is fixed at both the ends. Use Fe410 grade steel. Therefore, that is how the problem is given, right? Now, once even in the previous case also, that was the same end restraints were there. Therefore, from IS 800 2007, from table 11, from page number 45, already in the previous problem we have seen K, effective slenderness, effective length factor is 0.65. Therefore, the effective length is equal to 0.65 multiplied by 3.5. In the previous problem also, it was the same length. Therefore, 2.225 meters, not kilonewtons, right? Or 2225 mm as appropriate. However, it is a prismatic vertical member subjected to heavy loadings. Therefore, now what I'll do is I'll propose an I-section. I'll propose an I-section, right, to carry this much of ultimate load, 550 kilonewton. Therefore, for which what now I'll do is I'll go to this page number 44, table 10, student. What I am now, let me go to that, right? I am assuming H by BF greater than 1.2 and thickness of the flange 40. That is my assumption, right? Therefore, there, even the previous problem, that was the same assumption. Therefore, about the weak axis, the buckling class, about YY axis is B, even for the same previous problem, right? Therefore, now this is my assumption, keeping in my experience, because the load is PU, ultimate load is equal to 550 kilonewton. Therefore, now I am assuming a slenderness ratio, lambda is equal to 90. Whereas, if more is the load, then you assume the less slenderness ratio. If less is the load, you assume more slenderness ratio, right? Therefore, that is how I have assumed lambda is equal to 90. Therefore, lambda is equal to KL by R min. Therefore, even now I have KL is equal to 2225. That would be R min. Therefore, from that, now I am calculating what should be your minimum slenderness ratio. R min must be 25.23. Sorry, 25.28 about the weak axis or minor axis of buckling, like this. Minor axis of buckling. This is what called the minor axis. Therefore, now what I'll say is that either you choose a section where R min in any case not less than 25.28, one criteria, right? Even the other criteria is that right, for lambda is equal to 90 from page number 41. Now let me go to this page number 41, student, right? Let me go to that page number 41, right? This is how yes, right, this is how this is how the page number 41, right? I'm there in the page number 41. Design compressive stress FCD for column buckling about minor axis. About it is minor axis, it is class B. Therefore, there about this minor axis, it is class B student, right? Therefore, about that axis, now I have to have for lambda is equal to 90. Directly, I have to have the FCD value is equal to 134. Therefore, I'm just recalling that. Therefore, FCD from this table is equal to 134 MPa. Therefore, now we know that PD, load carrying capacity, is equal to AE multiplied by FCD. Therefore, how much of effective area is required? That itself is the gross area, which is equal to PD. Factored load to 550 divided by 134 is the permissible value. Hence, if I divide one with the other, I'll get 4104 mm square. However, because we are proposing the designs, hence I suggest that you increase the area by 25% to 50% more, so that the final section is okay. Otherwise, it may be requiring another iteration. Or if you want to optimize the section, you just start with the 25%, right? If it fails, you may increase to say 35%, or in the last iteration, you may increase by 50%, right? Therefore, what now I'm doing is that because the load is small, therefore I'm just simply proceeding with 25% increase. Hence, the area of the section proposed is equal to A required is equal to 1.25 multiplied by that area just required, 4104. It works out say 5131 mm square approximately. Therefore, what now I'll do? This is one criteria, that area must be 5139. Another criteria is that R min should be 25.28. Therefore, you keep in mind these two criteria, right? Therefore, now I'll go to IS 800 2007 table 46 student. I'll choose an appropriate section from page number 138. Let me go to that page number 138 student of IS 800, right? 138, right? 138, yes. And there in page number 138 annex H, right? Plastic properties of the beam side, or table 48 plastic properties of the beam side. Therefore, now you go on searching. What now we need to do, student, is that because you search a section where you have an area not less than 5131, therefore 5131. Therefore, if I go on searching like that, right, now I'm choosing a section ISHB 150. Therefore, right, I'm just going on searching, right? That is how I'm choosing a section ISHB 150, therefore, which is having an area of 3460. Sorry, I'm sorry, ISHB 150 at a unit weight of 34.6 kg is having an area of 4408 mm square. Therefore, 4408. Therefore, corresponding to that, I will note down the other relevant properties. The depth of the section is 150, and width of the flange is also 150, and the thickness of the flange is 9 mm, and thickness of the web is 11.8, and the radius of gyration 6.0, and about major axis as well as minor axis is 3.35. It is important for us, right? 3.35. Already what we thought previously what we thought 33.5, but it should not be less than 25.23. Therefore, 35.3 is greater than 25.28. Therefore, yes, it can be chosen. Therefore, this area, from area point of view, 4408, 5130 is the area furnished, right? 4408 is just actually it is less than this 5130. It may fail. I am just warning that it may fail. But keeping in my experience, I am just simply proceeding with this because I want to optimize the section. But as a student, don't choose this section. You almost choose a section which is not less than 5131 mm square, right? But however, it is just greater than the basic value, right? Basic value of without any increment, 25% increment, how much you require? You require is this value. This value is equal to say 4104. Therefore, I'm simply just proceeding with this. But as a student, don't proceed with this. You choose a section not less than 5131. Otherwise, you need to do another iteration because I want to optimize the section. I'm simply proceeding with this, right? 4408. Therefore, now for which even the slenderness ratio is okay about the weak axis. Therefore, what is the actual slenderness ratio is that 2225 divided by 33.5, which works out 67.91, which is it should be less than 180 as per this table 3 of page number 20. Let me go to that page number 20, student, right? Page number 20, right? Page number 20 is like this, right? 20, right? Yes. This is how that maximum effective slenderness ratio for a member carrying compression resulting from the dead and live loads, because no data is given, therefore I'm assuming so, therefore it is 180. Therefore, what I now got, the actual slenderness ratio is approximately 68 is less than 180, therefore it is okay. This is okay. And so even this roughly 67.9 is less than 90 slenderness ratio, what we assume, therefore it is okay. It is okay. Therefore, now I'll go to this table 9b, because about the minor axis it is buckling class B. Therefore, now for slenderness ratio 60 and 70. Let me go to that page number this page number 41, student. Just wait for a moment, right? 41 means this is that, right? Therefore, for the slenderness ratios, what is the slenderness ratio? 60 and 70, right? For 60, 181, 70, 166, 60 and 70, right? Yes, 60. Yes, for 60 it is 181 and for 70 it is 166. Therefore, now I'll interpolate. Therefore, for lambda is equal to slenderness ratio is equal to 67.91. It is how much? Therefore, that is nothing but 181 minus 181 minus 166 divided by 10 over a difference of 7.91. It is how much? Therefore, that now works out. FCD is equal to 169.14 Newton per mm approximately. Therefore, the load carrying capacity about the minor axis is equal to effective area multiplied by FCD. Effective area is 4408 multiplied by FCD. FCD is equal to 169.14. That will be 10 to the power 3. It works out say 745.54 kilonewton, which is much greater than 550 kilonewton. About the minor axis itself, what we are now doing is I am calculating about minor axis. Therefore, my section is okay because I have calculated about minor axis, whereas I need to target only 550, but I achieved 745.54 kilonewton. Therefore, even you may further optimize the section. From I-Section 150 section to a lower section also, right? Lower section also if you wish, and also simultaneously it is satisfying the slenderness check also. Therefore, now I'll say that my final section is this I-Section 150 at the rate of 339.4 Newton per mm square. Having these properties, right? Now let me go to that from page number 138, right? 138 means this is my final section, student, right? This is my final section from 138. Yes, I-Section 150 having these properties as the final section, right? This right, I-Section 150 as this one. Or if you wish, you can try with another lower section, which is having just area, or even you may try with a section I-Section a lower section, but I don't find any lower section than that of I-Section 150 because HB sections are generally used as column section, student. Therefore, I don't have a lower section in I-Section lower than that of 150. Therefore, I'll stick with I-Section, which is the column section 150 as my final section, as my final section, right? That is how the first problem we have seen, wherein a section was given, then we have calculated the load carrying capacity, right? That was governed about the minor axis, whereas in the second problem what is given is load is applied of 550 kilonewton like this, where we have no fixed. We have proposed an I-section, even we have made a check for load carrying capacity as well as the slenderness check, right? That is how the designs of the columns like this are that of the stanchions subjected to compression load, right? Then I hope student you enjoyed the discussions, right? If you have really enjoyed the discussions, don't forget to click like, subscribe, share and comment over YouTube channel, right? In the next class we shall see the design of compression memberized strut, wherein we will try to design a single angle strut subject connected to one side of a gusset plate, right? Till then, bye bye student.